Good morning. My name is Susy Webb, and I am a senior printed circuit board designer for many, many years. And I am here to talk today about designing signal return path. Before we start, I wanted to mention that I have a cold, and unfortunately I will have a cough drop in my mouth the entire time. I will try not to cough, but unfortunately I may do so. Also, we have, you're welcome to ask questions. They will be answered at the end, but you're welcome to send them in as we go along. And there is a service that Altium has where you can subscribe to their channel, their YouTube channel, and be able to get lots and lots of different information off of different webcasts that they have provided for you. With that, let's get started. So the first thing we have to do when we're understanding about the designing of the return current is figuring out what happens, and so we have to talk about the physics involved. And the physics involved, can we stop just a second? Okay, we're back. Sorry about that. Little technical difficulties. So what we need to do is understand what's happening with the signals so that we understand why we need to design the return path. So that's what this first section is about. It's about the physics that are involved. So when we have signals that are turning on in the board, they are changing state, and that is creating the current, the voltage. I'm sorry. Let me calm down a second. That is changing the current and voltage, and they create magnetic and electric fields. Those electric fields, as you can see here, are what are on the around every single trace that's turning on and turning off in the process. And as you can see, there are other traces around it. There are other traces around it, and those other traces can be influenced by the signal changing state. So we need to be careful what we're doing with the designing of the circuit boards. These fields are always present, and there is much of the designing that is about containing these fields and making sure that they are in the smallest area possible so that we don't have issues with them interfering with anything around them. A plane layer helps. We put plane layers close to every single routing layer, and that helps to contain that energy. As you can see down here, the energy is contained within the trace and the plane very well. But if it's on an outer layer, the energy can escape to quite a large area. So putting another plane layer is actually beneficial as well. So burying the traces inside the board rather than putting them on the outer layer is best, especially for high speed and anything that's a problem signal, a signal that we need to be sure to guard with. So that is one thing we absolutely must do, is put those signals on the outer layers of the board, inner layers of the board, sorry. When the oops, go back, thank you. When contained, the energy will have less ability to interfere with any other signals that are on the board, and when it can't interfere, of course, we have the good clean signals that we would like to have. So the return path has to be planned by the designer who is designing the board, just like the signal path is. Most people go in and they think about the trace connections from here to here and how they're going to make those connections and what layers they're going to route to, but they forget sometimes about how that return current is going to follow that trace when it goes back and forth. So that is the important part, that we have to understand how those traces are going to, how that return current is going to get back to the source as well, because it always has to get back to the source, and it will find a way. Since the return current will flow in the nearest copper, we have to consider any copper that is nearby. That can be signals, that can be planes or other layers or whatever, so we have to be very sure that we understand that. So in designing a board, the designer always has to be thinking, how is this signal return going to get back to its source? The way to plan the return path is to set up transmission lines, where the signal is the difference between the trace and the return path measured at any point. And so the signal is going out on one layer and it's coming back on the other layer. Now it's coming back constantly, and I'm skipping ahead of my slides here, but it's not just a one-time thing. So you understand that you're giving it a good path by putting a plane close by. The transmission line, that is the single signal and its return path. So you need to know the relationship between the signal and its return path wherever you're taking it through the board. Where does the return flow? The low frequency energy follows the path of least resistance, and that is, it can spread out anywhere that it has a low resistivity on the board, which would be a plane as well. But when you get the higher frequencies, that energy is going to follow the path of least inductance, and so it will try to follow the path exactly. Several people have set up an example to prove this. This is an example where there are there are connections made here with a long wire that goes between them and a short wire down here that is connected between them. The procedure that they have followed is to put some energy onto one of these things, one of these ends, and see what happens as far as where it goes back to the source. So it would follow the path around here to the load, and then would it go back through the short path or would it go back through the long path? And the answer is, based on this information from Dr. Bruce Archambault, it depends on frequency. The example trace that we're showing here is the picture in the previous slide here. And then the energy has been put into it here, and at the current density is at about 1 megahertz, it looks something like this. At about 10 gigahertz, it looks something like this. At about 1 megahertz, you can see that the signal is and its return are already following each other exactly. So they're not spreading out like they would do here. They're not using the little short path that was given to it over here. They're completely using the return path that is closest to the part itself, the signal itself. We're making adjustments here, sorry. So that helps, yes, thank you. The electromagnetic wave is what is being produced by the electric and magnetic fields. The high frequency energy fields move in dielectric material. They don't move in these copper, despite what many people think. They are not in the copper themselves, or if they are, it's only by just the tiniest of skin effects. But the trace guides the wave, which is flowing in the dielectric material between the signal and its wherever it's going, its load. The current flows in the loop that is constantly moving forward and returning to the source all the way down the path. So as you can see in this picture, the signal is flowing forward and then returning immediately. And it does that immediately as it goes all the way down the path. It's flowing and returning all the way down the path. So it's very important that we have it it's set up so that there will be no gaps in that split in the signal and the return path, so that everything works just fine all the way down the signal. The energy fields can spread based on location. The outer layer has air on one side, and that allows the fields to spread more than the inner layers. So we don't like that. It gives more chance of possibility of antennas and of noise created to anything that's around it. So we try to keep that very, very minimized by routing anything critical and anything high speed on the internal layers of the board. It's quieter there because there's better impedance control there, and all of the energy cannot escape out of the plane layers that happen to be on the outer layers of the board or between those layers and the outer layers of the board. The signal layers should be as close or closer to the return planes than any other signal layers. The fields may spread based on the design. There may be problems with the signals and the return path. If one of the more common sources of noise, crosstalk, ringing, interference, all kinds of things, all kinds of problems can happen because of the energy escaping from the path that we want it to take. The signal may take unintended paths, like other traces may be too close that cause the signal to spread to those signals instead of spread to the return that we want them to take. It may be that the via inductance is too high or not used properly, because if a signal only uses a portion, a high-speed signal only uses a portion of the via but not the entire via, then there's a potential for a stub there if it's a very high-speed signal in a thick board, and that could cause an antenna issue as well. Or if there happen to be cables nearby, all kinds of things like that can cause problems with the signal and its return path. The highest frequency signals, which are the fastest rise time, will require the most care and the most energy to figure out how to calculate where to put those in the board itself. What determines high frequency energy? That would be the rise time, the rise fall time. That is the time required for the signal to rise from 10 to 90% of its amplitude, or to fall from 90 to 10% of its amplitude, the DIDT of the signal. The faster rise time signals spread out more high frequency energy. So the higher the frequency, the more possibility of bleeding over into something that's nearby. The higher voltage signals with a fast rise time also spread more energy. So for example, if you had a high speed 5-volt signal, it would be giving more energy away than a high speed 3-volt signal would. Rise time is important to the return because the rise time is the actual, it's more important than the clock speed because it's actual time that indicates how the circuit is actually working. And when we're working with the rise time, we actually take the clock speed and figure all the way up to the rise time as far as the bandwidth that we need to be concerned about for what the speed of the circuit is. So this is the circuit, the frequency of operation that the circuit is working at, not necessarily the clock speed. It's much more important than the clock speed that we understand the rise time. And the rise time can be gotten from either the data sheet or from IBIS models and things like that. So where do we cross over and say that we are in a high-speed environment? Lee Ritchie, this is a quote from him, the bottom line, and it says, if it's current technology, it's high speed. And what he means by that is pretty much everything out there that we're working with today is high speed. There are some things that are simply not as high speed, but if you design your board as if everything were high speed, then you are not worried about something failing because you didn't design it carefully enough. So it's always a good idea not to over-constrain the board, but yet to design it as if it was high speed. The concern with return is largely a crosstalk interference noise one. Crosstalk increases when the traces are far from the planes in the stack-up. We want them to be nice and close to each other so that there's lots of default way, low impedance way for the signal to return. The traces are, if the traces are farther from the return path, that's a bad thing. They would be lower in capacitance. There's increased impedance for those traces. And so we always need to plan the stack up to see how we can set up a really low impedance return path, because the signal has to go back to its source. And in doing so, it will find a way. And if it finds a way that you don't like, then of course that's going to interfere with other signals on the board. So if using ground planes for return, the number of planes needed will partially determine the layer count on the board. It's always a good idea to place a ground plane next to every power plane on the stack-up, That helps to not only be a place for the signals to return, but also the power, any stray power energy that is on the power layer can then return via the ground plane as well. And then it's good to have a ground plane next to every signal layer in the stack-up as well for return path. And usually it's not a good idea to split the analog and digital ground planes, and we'll talk about why in just a few minutes. What is crosstalk? It is the transfer of energy in an active source to a victim circuit. It increases the energy on the non-intended return paths. Edgewise traces, these traces here, these traces here are edgewise. They're next to each other as opposed to on top of each other. And those traces are have some amount of coupling between them just by the fact that they're turning on and then next to each other and whatnot. Broadside traces have even more possibility of cross coupling one to the other, and so you can see that you would want to avoid this at all possibilities, and so this is why we don't route traces one on top of the other in the same direction. So if you have to put things next to each other, I mean on top of each other going in the same direction, offset them by a little bit as much as you can so that they don't end up coupling to one another like this. Some crosstalk related guidelines use logic that is no faster than you absolutely need. Use the lowest clock frequency possible. Use the longest rise time possible. Slow any fast rise time with termination resistors. Keep the signal loop area small in the design. Control spacing, especially around the clocks and the high speeds and the differential signals. All of those things and more are related guidelines to what you want to do to make sure that you are minimizing the amount of influence that you can get to other traces from the signals that you are actually designing. So some high priority signals would be clock signals, memory, switching digital signals, A0 and D0 over A15, usually because of the way they're set up. It depends on which one is set up as the one switching most often. Periodic repeatable signals like chip selects, those kinds of things are all switching power circuits. All of these are things that can create noise easily, and if they create noise easily, we have to control that noise and keep it contained as much as possible. Some victims that we have are signals that switch on a small voltage swing. They turn on and off easily. If they turn on and off easily, they can get some noise, and that can turn them on or off depending on what we are doing. And we didn't want them to turn on or off, but the noise caused the signal rate, the signal height to go up enough that it would cause a problem with it. I/O signals on the connectors to the outside world are a huge priority because anything that goes into the outside world from the board can create an antenna outside the board. For example, if it goes out through a cable and that cable is now a long piece of a dipole antenna, and it can cause real problems doing so. Analog signals, of course, would be a victim because they are a single voltage, single signal, and as such they don't have the entire bandwidth that the digital signals have, and so they're easier to mess those signals up. Analog I/O gets even more high priority than the digital I/O just because it's just more sensitive. And so we would place and route all of these victims early because we don't want anything to interfere with them. When we are dealing with the return current, we need to think about the parts that we're selecting and putting on our boards. If we don't have any control of that because somebody else is making those decisions, so then we need to at least share our information as to what we believe we understand about the way the parts work and don't work. For example, the part down here, the part down here has worked for many, many years. It's a typical SOIC pattern with the power and grounds in the opposite corners. And it worked great for many years when we did not have the really high-speed signals. But now if a signal routes into the upper regions of these lower regions here or the upper regions here, it has a long path for the signal to the return current to have to go and find the ground pin or the power pin that it's returning on. And so that's not as good a method to use as opposed to using something like this one over here, where the signals all have a close power ground pin to return on. The same thing goes for the BGA in this corner over here. The green balls are the signal pins, and if you have signal pins coming in on these corners down here, then they have a long path for that energy to be separated from the return path that is going over to the inside of that part. So it is best to choose parts that have more of a spotted thing throughout, where the power and ground pins are put throughout the part, so that any signal that's referencing a ground pin will have a ground pin fairly close by, and anything referencing a power pin will have a power pin close by. I mentioned that we would talk about the splitting of the ground planes. This is a set of slides from Dr. Henry Ott, who is one of the gurus of EMI. And he has shown in these slides that sometimes people want to separate the analog and digital planes by separating them physically. And he's saying if you keep them far enough apart from each other, there should not be any problem with them overlapping each other, because you just keep them back from the edge, the digital signals back from the edge. The digital signals are going to follow the signal itself, so the return current is going to be where the signal is. And the analog, if you put it up in the analog region and keep it back from an imaginary line between them, then the two should not interfere with each other, and usually don't interfere with each other. If you have any concerns about that, you can also route them in opposite directions. For example, if you have the analog in routing basically in this direction here, then you might do the digital in the opposite direction. The digital is going to stay, the digital return is going to stay with the digital signal, and so it has no reason to spread out. And even if the analog spreads out, it has no reason to spread out all the way down to the digital area of the board. If you ever decide that you must split the power and ground planes, then be sure that you don't split over the edges, that you don't overlap the edges of those planes, because the edges of those planes, for example, the blue one here, could easily have some noise in it that would couple down to the pink one here. And the same thing goes for this section here, could capacitively couple energy up to this one and this one over here. You don't want this capacitive coupling, because this is some stray energy, some common mode energy that could cause problems on the board in signals that are referencing those planes. So you want to, if you ever do separate both planes on the setup, then you want to have them not overlap each other, so that they don't have an issue with any of the stray energy interfering with something else. And when you do this, tie all the like planes together in your stack-up. So if you have lots of ground planes in your stack-up, tie all of the ground planes in your stack-up together with through-hole vias, or with a setup with HDI vias that set it up so that each of the planes are tied together for the same potential throughout the board. Signals that are routed between more than one plane, the return will always take the easiest path. It's always going to take the easiest path for that signal at that frequency. And if the signal flows between two of the same planes, same type of planes, both grounds, and they are equal distance from each other, then it will split the energy all between both of those planes. If the signal flows between two planes and they're not equidistant, obviously it would flow to the one that's closest to it, because it doesn't want to work that hard. Basically, it wants to do whatever is easiest. So it's going to flow to the one that's closest and easiest, but some of it would be down there on the other one as well. If the signal happens to flow between two planes and one is broken, then that signal, at least at that point, would go and flow only on the one that is the solid plane. That's where we would want it to have the least interference, and so that's what it would choose to do. Not that it makes a choice, but it would flow in the easiest path that you're giving it, and that would be the unbroken plane. If the signal routes between ground and power planes, then it will return mostly on the ground, because it's going to, if the signal is returning on ground throughout the board, and then it comes to this area where it is between a power and ground plane, it wants to return to the ground pin of the device, and so it's going to flow on the ground side of the signal and ground pin planes. So consider when the signal and return are, every time you're placing a signal in the board, anything that you're routing, you want to consider where those signals are going to go, how that signal is going to get back to its source. Many of us, me included, like to fill the outer layers with power or ground planes because it's good for containing all of the energy that's flowing inside the board. When we do that, there may be signals that are on layer 2 that are now returning not only on 3 but also on the underside of 1. And so we need to be sure that when we're doing that, if they're specifically returning on 1, that they don't go into the no plane areas, because that is basically crossing a split in the plane, and we don't want that to happen. Signals must be carefully routed on 2 to contain within that area, so that we don't, basically it's crossing a split. If impedance controlled, the impedance would change also. So if you have signals that are on 2 and they're basically set up to return on 1, and you've impedance controlled them to return on 1, then if they go into that open area, you're going to have a problem with that impedance control as well. A bit about the power layer. It is okay to route signals that return on the power layer if the signal is the same voltage as the plane, the power connected to its driver, if the signal does not change layers at all, if the signal only changes from one side of the power plane to the other side. But that's not a good idea, because as I mentioned, you want to have every power layer patterned with a ground layer, and so that's not a good idea to have it change from one side to the power layer. But it could work if that's what you're setting up in your stack up. It's just not the best idea. And if the power layer is paired very closely with a ground plane, that's a good way for the signal to return. And we'll go into all of this with pictures later that will help you see how this is a good thing and to do with the designing of the signals. The signals will return to the power pin of the device and then move to the ground pin internally in the device. It's a very short, very quick path for it. Capacitively coupled across, and have no problems with that. So it is okay to use the power layer if these qualifications are met. The digital signal will return on the closest plane no matter what the voltage is. I mentioned earlier it will return on anything that's close copper-wise, anything, and that could be signals or that could be planes or whatever. But when you put a plane, when you put a signal returning on a plane in the stack-up, it's going to return on the closest one. It does not care what the voltage is of that plane. It's the easiest return path, because the energy cannot penetrate through a voltage plane to get down to the ground plane. I had an argument with an engineer at my company one time. He said, oh, he will pass through the via hole antipads and get down to the ground plane. And so he wanted me to set it up in a manner where the signal that was on, let's say, layer 1 here, was returning on ground. And in fact, it is not doing that. It's going to return on the voltage layer 1 layer down, and that is going to be a problem, because if that voltage layer is not the same voltage as that signal is, then you get creating noise from one to the other. When possible, use solid planes, not routing for power. Some boards will allow you to route with power and work perfectly fine for the power distribution, but it may not be the best return path for the signals if you're planning on using that for power for return. So be careful with using that and try not to do it that way. If you're using that layer for return, then you want to be sure that it can return on a solid non-meshed plane. You see the mesh plane below? especially large mesh grids can be, that's hard to say, large meshed grids can be a really big problem for signal return because the energy has to spread out as it's traveling across that. If a signal was routing against this plane, returning against this plane, and it had to cross over a large mesh grid in particular, the energy of the return would have to spread out at each one of these little mesh openings, and so it can create quite a problem with that signal. So you want to be sure that you don't use meshed grid planes if you don't absolutely have to. And I know there are some industries that feel they need to, but if at all possible, maybe they could have a solid area underneath the critical signals rather than having the mesh area. The spacing between the planes, it should allow for several times h, where h is the distance between the plane and in the next plane down. That will keep the energy contained within that area. It keeps any stray energy from trying to couple across that opening. We don't want any energy that's in here to couple across to here. So we have to keep an opening that's wide enough here so that energy cannot couple across. The shape of the return energy is like a bell curve under a trace. The space is needed to keep not only for the traces manufacturability, because we want to be able to manufacture the traces easily, and putting them too close together can cause manufacturability issues. But we also want to be keeping them apart from each other because we don't want those bell curves to overlap one to the other and create any kind of noise between those signals as well. And here's an example of that. Where we have a signal that was routed right along the edge of a plane here, and a signal just on the other side that was routed right along the edge of that plane. And this is, of course, two layers. You're looking at the signal layer in the red and the return plane in the green and the blue. And the signals will then be very, very close to the edge. Their bell curve can't be contained, and so this energy that is not contained has the possibility of bleeding across to the other plane and the other side of that opening. So this is not a good way to do it. Try to keep some distance outside that signal on the return area of that layer. For routing and return, remember where the energy flows. The low frequency energy will spread out, something like this over here. It doesn't care where it is. You have a signal that's coming from here and routing around to this particular device. That energy is going to spread out all around that region of the board because it has nothing to contain it. It is the path of least resistance. But once you get into the digital signals, remember they will flow exactly underneath the signal itself on the closest plane layer. So that is talking about that, so that we can go back into this and say that when you route signals between, let's say, via patterns, there's a via pattern here. And we want to be sure that the signal, not only the signal can flow between the via pattern here, but also the return current can flow between the antipads of those vias, which are I can't find the there. So the antipad opening needs to be small enough, if you will, or the pattern of the vias needs to be wide enough that the signal and the return path can flow between those two openings. It sets up a pattern that can help routing on any different layer of the board, because these are through-hole vias in this case, and it will set up a pattern that can be used in any east-west routing that you happen to be doing on that board. You may or may not be able to put in smaller antipads depending on your IPC standard that you're working with. And if you use HDI technology, it will impact fewer layers, because your HDI signals are only going down, vias are only going down a couple of layers probably, and so you don't have to worry about the openings on many layers, only on the ones that the HDIs are open on. Think about the routing possibilities and make them as smooth as possible for ease of return. In this case, what I have done is some what we call S routing, where the signals actually come from here, and they make basically an S pattern and go around, whoa, go around to here. And that helps because there are no vias in those particular areas to block anything else, any of the other routing. It's very, very good for the signal integrity. It's very good for the routing return integrity, because if you have a proper plane set up underneath this, everything can flow very naturally from one area to the other. Up here we have some signals that do go through vias, but they are contained as much as possible to the routing method that will keep the fewest number of vias on the other layers of the board, and that helps any kind of routing on any of the layers of the board. Try to route a bus as one entity. Look for ways to route on an entire bus on a single layer or a layer pair, and I'll talk about layer pairs in just a minute. And internal layer is best for routing because it contains all the energy, and there's less possibility of things interfering with other things when they're on the internal layer, because the energy has to go through dielectric material as opposed to going through air, where it can more easily flow. It's good for signal integrity and routing channels. It's great for return when you do it in one entity, because there's only one place layer that is containing the energy, and you don't have to worry about different environments, and I'll show you what I mean with the next slide. Each member of the bus is exposed to the same environment. So what I'm talking about here is if you have a large bus with many byte lanes, you can do some of those byte lanes on one layer, let's say the blue, and some on the red layer, let's say. And if the blue layer and the red layer happen to be on either side of a plane, not throughout the stack up, but if either side of one plane layer, they're both getting the same environment, and they're both returning on the same layer, which will take them back to the source easily. And so this is a best way to route a large major bus, is to keep them on opposite sides of the same plane layer. And that is one of the things that we do with layer paired routing, and I'll talk about that more in a minute. When you take routing and change it to other layers, when a high-speed signal or bus changes layers, you want to place ground vias. If it's referencing ground, you want to place ground vias at the ends, because the ground via here, the ground via here will help the energy to return back to the layer where it came from. We've changed layers with this signal, and we want to be sure that we have a good return path that we've created for it. By putting a ground via close by, you'll be able to very easily move that signal to another layer that is referencing ground as well. The energy spreading distance to the via becomes very small because it's very fast. And any benefit from a ground return via will only be realized if the ground return via is very close to the original via. And that is a quote from Dr. Bruce Archambault. So in other words, what he's saying is, if you're going to put these vias in, you need to put them in very close, because that's the way that it helps the signal the most with its return back to its source. And here's an example of where some vias have been placed in onto this routing in this part. You know, all of these blue vias in here are probably ground vias that I've added. They were either within the device itself, or they were added in to be sure that there were lots of vias close by to any high-speed buses that happen to be in that area. It provides a good return. If you're going to route with HDI, it's always very important that you continue to think about the return path for HDI. Lots and lots of information that we get about HDI out there says, you know, oh, you can do it in this many layers just by routing on this layer, and then this layer, and then this layer. But the truth is that you have to have a return path for every signal on HDI as well, and so you have to be sure that they are not overlapping each other. For example, in here you've got some signals that are routing over signals or pads, and so we need to be careful that they don't do that, because they're creating the possibility of crosstalk and noise, and we don't want that to happen. Because all of this is so close together, we don't want to have to be concerned with the way we design it causing it to be a problem. Since the HDI uses thin dielectrics, it can very easily couple from one of these pads or traces to another one of those pads or traces in the area, rather than coupling it back where we want it to go to the return. HDI generally has lower noise because it has better signal integrity because the traces are so close to their return layer. But if you don't pay attention to how you've laid out the structure for the HDI, you could have more possibilities of problems rather than fewer. So if you're working with HDI, try to set up your return path in a manner that will help you get the most plane layer underneath it. For example, VN pad has very good plane possibilities because the via is in the pad itself. There are very small anti-pad openings, and all of this black area could then be grounded. Or there's an area here, a way of setting up the HDI here, such that there's lots of green area, which is the ground plane, and lots of signals can return against that green area without causing problems. If you have lots and lots of routing that you're working with, and you may need to set up a more complex pattern, set up a pattern that allows for lots of routing on the ground layers that will be solid ground plane, and so that you have good return for those. So even though you have lots of signals in this area, if you have lots of plane in that area, you have good return path for all of those signals. Think about HDI routing with crosstalk. As the signals get closer to the planes with HDI, they may also be getting closer to each other, and of course that creates more possibility of interaction between them. Not just having this as a good thing, but having more of this as a difficult thing. Other signals and traces can be potential return paths, and HDI microvias reduce crosstalk because they can't contact fewer layers. So we'd like to use HDI for fewer layers, and because they're nice and close to their return planes, if they're set up properly, they will work very, very well. If they're set up improperly, there may be problems even greater than with regular vias. Return separation for through-hole and HDI. Be sure that the signal returns inside the BGA is not blocked by lots of through-hole or microvias and their anti-pads. For example, the ones on the left here have plenty of room to return in this particular area, and so do the ones in the middle. But over here on the end, we're getting to where we're actually chopping into the anti-pads with these return paths, and it's not as good. Even the slightest bit of overlap done enough times can cause common mode noise, which can cause EMI problems or noise on your board problems. And so we want to try to set up everything to where it's evenly spaced and not overlapping even the anti-pads of those parts. For differential pairs and their return, the current flows separately on planes under each trace. This is a quote from Dr. Howard Johnson. The current flows separately on the planes under each trace, almost as if they are two independently routed single-ended signals. So Howard Johnson is saying that the energy, the return, is flowing in the plane, not in between the two. Here, the differential signals on layer 3, the red that you're looking at is layer 3, and point A is back in here. Return on the underside of the power plane on layer 2, which is the pink layer right in here. The divergence at point B, which is here, is where it creates two single-ended signals that go into these devices over here. Here's one of them, and here's the other one over here. Clearly, the return current associated with each signal flows separately on the underside of the power plane, pink, hugging tightly to the trace, following wherever it goes. So this is all information from Dr. Howard Johnson. So the point of this is that the energy is going to be underneath, above these signals, in this case, on the plane layer, and then as they separate, it will still be on the above, but it's keeping it per the trace, not per the differential pair. When you're changing layers with differential pairs, it's a good idea to put a via close to the ends. If you have a pair and you have room, go ahead and put a return via at both sides of those differential pair signals, and at both sides of their vias, and that will allow for a good return path for the energy for those signals through the ground plane as well. And we'll show you why in a little bit, why that's so important. Also, you can do it this way where you have one, and this might be easier if you're dealing with a really dense board, to put one ground via for the two vias of the differential pair. Either way helps, but you don't want to have just one over here because it creates a difference between this signal of the differential pair and this signal of the differential pair. You want to have them equal. Everything as equal as possible for the differential pair. Sometimes people run out of routing room and they think, oh well, I'm just going to put a few routes on the ground or the power layer, and then that'll settle my my ability to get the board routed. But the problem with doing that is if you look at this picture, you're dealing with a layer that is green, that is a signal layer, and the layer that is more of a pinkish color is a power layer. And if all of the green signals are trying to return on the plane that is pink, and they are cut up by the traces that were routed on the pink layer, then it's the same as if those signals were crossing a split in a plane, and that energy will spread out because it cannot cross, it cannot follow the signal the way it wants to follow the signal, and so it will have to find another path back to the source. In doing that, it spreads out largely, and it spreads out into areas that we don't want it to go to. It's called unintended signals, and so we want to keep all of the routing on any kind of a return plane to an absolute minimum, and then only put it in areas where it does not have anything that it's blocking on the layer that's returning on that plane. Other questionable return paths would be anything that increases the current loop area between the signal and the return. This would be things like an unshielded cable or connectors, signals that change types of reference planes, especially if they are sensitive or high-speed signals, signals that must return to their own source, the board ground to the board ground and the chassis ground to the chassis ground. So if you're trying to build in a chassis ground area into your board, and you have parts that are routed within the chassis ground area, for here in this case the green, then you would want all of the energy contained within that green area, so the return current would go back to the ground in that area. And then once the signals have come out of the device and are going into the board ground in the blue area, then you would want all of those signals to return against the board ground, the blue area, and not overlap the two. The only time you overlap the two is if you have a filtering device that would bridge the gap over the two of those parts. Controlling the return current. To plan for the return, follow the routed path on the adjoining plane. Find any kind of splits or dams or antipads, etc., and find ways to make the changes. So you want to design the return at the same time you design the signal. You want to think about what you're doing and how you're routing it and where the signal is going to get back. But after you have designed a certain area of the board, you also want to go in and look at what you have done and what the return possibilities are on the other layers, and you want to make sure that there is at least the width of a signal in the return plane, and 3x the trace distance to the plane is the best, per the rule of thumb that I mentioned earlier. So, for example, here is a board with, you're looking at just the vias, the through-hole vias, and the return plane, and you're looking at it to see what you can see as far as splits and dams and things like that. For example, here there's been a column set up for signals to go north-south in through this region. Here they cannot go east-west. So if you have signals routed east-west, you'll have to take those signals to another layer or move them or change this particular pattern of vias that are in this area. Here you've set them up into a good pattern to allow those signals to go north-south and allow the return path to go north-south. Here's a good indication of what you can do with a BGA just by the X pattern that you can see. This is just the vias that you're looking at, and yet you can see how the energy will be able to get into and out of that particular part for power distribution and whatnot. So this helps you see when you've made mistakes with the routing and the vias that you've placed already, such as this particular example, where you can see there are no channels, no power, pardon me, there are no channels, no power ways to get the signals from one area to the other. And so you will have to be wiggling those signals all around to get the energy and their return to get through these areas. So it's best to set up a pattern so that they can easily flow from one place to the other. Can you stop just a second? Okay, we're back. Sorry about that. Had a little coughing problem going. So the point is, you want to be able to look at the pattern and see that you have a path for your signals and their return path. When you're setting up boards, like daughter boards and mother boards, into a system, and you're taking the same ground from one to the other, look at the way that they're going to align with one another and make sure that you can do it in the best way possible. For example, on the daughter board here, you have a ground side, and the ground plane here would then, the signals that are referencing that ground and the ground would both be returning in the best path right here. If you're on the other side referencing power, then the signals would then come down straight down here and come across down here, as opposed to trying to intermingle them in some kind of other different way. So think about the easiest way and find the most direct path for those signals and the return to get from one layer to the other in your whole entire system. Do not count on the app notes to suggest routing to have considered the signal return path. They probably won't, and you will need to think about that yourself. Do not count on the auto router to have considered return path if you put something into an auto router, because it doesn't think about return path, it doesn't know about return path, and so you may or may not be able to clean that up once it has routed those sections of the board. You want to use short traces, especially in areas sharing return and power connections, because you don't want them bleeding over from one to the other. You want to use differential signals when possible, because that is the nicest, cleanest way for the signals to route from one place to the other. And spread lots of ground vias throughout the board. And if you're using power and have multiple power layers, spread lots of power vias throughout the board so that there's a good path for the return of those signals, and the potential is the same on all the different layers of the board, all the different ground layers or all the different power layers. Splits create a separation. We never want to have separation between the signal and its return. Every time a signal routes across a split, there is a potential for that energy to find a different pathway back to the source. If it finds a different pathway, it's going to be someplace that we did not want it to be. Signal return energy can't follow the signal, and it will spread out trying to capacitively couple across this opening. If the opening's too big, it won't be able to couple across. So how will the energy of the signal that is going, the red signal that is going from here to here, how will the energy get across that opening? Well, number one, it probably shouldn't be, because it's a different voltage. These are two different voltage, either analog and digital, or voltage A and voltage B. So the signal probably shouldn't be routing around that area in the first place. But if you do happen to do something like that, you have to understand that the signal energy is going to try to capacitively couple across that opening, and in doing so, it's going to spread way out across that whole split in the plane, and it can easily cause an antenna to occur. And the antenna, of course, can cause all kinds of problems with everything around that board. For example, here is an example where there were two signals that were routed across a gap in the board, and one of those signals is an active signal. That would be the one that is the one on the one on the left, or my right, I'm not sure. And then you can see in the other signal that it's actually picking up a lot of energy as well, just by the fact that the one signal could not capacitively couple to its return path and had to jump somewhere else. So both of these signals are lit up as if they are active, even though only one of them is active. Plus, look at the energy that is in the split itself and the ends of the split, and you can see that the energy is quite spreading out, causing all kinds of issues. And if you think about this and any other signals that happen to be in that area doing the same thing, all of those signals have the potential of getting all kinds of noise on those signals. Dr. Todd Hubing says that any signal can create noise even up to an inch away. You can realize that energy in an area that you didn't want it to be in. So it's a good idea to always be careful about routing anything across a split in a plane, and always understand why, because it's going to create problems with everything else in that board. Here's another example, and even though the split only goes a short area, it's the white area, that is the split in the plane, and even though that split only goes a short area, you can see from the energy around it that it is creating energy all over that plane of the board, and that's a problem, of course, because you don't want to have any energy creating problems with the other signals. And look at the red that's going across, well, I can't get my angle right here, the whole trace itself is lit up bright red because it's trying to find a way to get across that opening. And it's not only important to understand that the fields will spread in the XY, but they also spread in the Z-axis. So if there's something above or below that trace that is easier return path for it, that's the path it will take. So you want to be sure that what you're doing is containing the energy and not causing a problem for anything that's around it. Here, there's an example. Some people would like to put capacitors across that split in the plane to help with the energy to cross that plane. The problem with that is that the inductance of those capacitors is such that the energy cannot easily the high frequency energy cannot easily flow through them. The low frequency energy can, and that is not a bad thing. It's a good thing, but the high frequency energy will have to be finding some other way because it simply can't find a path across that. The caps are too inductive in this, and the energy can't go through them, so they can't find a path back. So we would want to find a different way for that high frequency energy, and the only way to do that would be either to capacitively couple, which we talked about is not a good path, or simply not routing a trace across a split. It's just not a good idea, especially with anything high frequency or critical or anything like that. There are occasions when it's not a critical signal, when the energy, you see the signal in red here, is routed next to a return plane, and there is a split in the return plane. If that split in the return plane happens to be very, very small, the energy can capacitively couple down from the ground plane to from the power plane to the ground plane and then back up. If the distance between the power and ground is very, very small, and if the spacing between the opening is very, very small, it can do this. But it's not good for your signals, and you would not want to do this for any kind of high speed or critical signal, because you don't want to create any potential for problems for those particular signals. And if both planes of the pair are split, you never want to cross a signal with a signal at any frequency. Signal crossing splits can be a major source of common mode noise. The single-ended nets with poor return, no return for instance, no return pin close on the part or crossing a split or whatever, or if the differential signals are with problems, unbalanced vias, crossing split planes, etc., then you can convert significant amounts of current to common mode energy. What is common mode energy? It's basically stray energy that floats around in the board, coupling to whatever it feels like, basically, in order to get back to its source. All energy has to get back to its source, and it will find a way. The currents must return, and they will find their own path. And I jumped ahead a little bit. They will find a way. Even signals that happen to have spread up to other signals have to then find a path back to the original source of that particular IC, and they will find a way. It will be very, very low energy, but it will be still something that could couple together with other energy and cause some issues. So the sum of the conducting, common, and displacement currents that return in the source must equal the output current. So when you have a signal that turns on, you have to account for all of the energy, not only the signal and the return, but also if anything bleeds over to something else, you have to be aware that it's going to have to get back too. So the point is to keep everything far away, not to figure out how it's going to return. If you have a fully split plane and you happen to route something across that split, for example, the red signal, and they're only connected in one place, this case the power source, and the trace crosses, then you would have low frequency energy that would have to flow from one side all the way back to the power source and then back to the source of the signal. Low frequency energy could possibly do that. High frequency energy would not be able to do that and would have to find a path back to the source, and you have no idea what that path is going to be. So you never ever want to route that way, because you don't want to have signals that have to find a path. You keep your trace routing as localized as possible. Short traces have fewer problems. It takes a while to build up noise, and so if the shorter the traces can be, the better the possibility of having noise is. And even without a split in the return plane, traces must stay local to their area. You don't want to route a digital signal in an analog area. You don't want to route a +3 signal into a +5 area, because you're intermingling their noise that are on their planes and their return paths, and you don't want to get any possibility of noise coupling from one thing to the other. Energy can couple from digital traces to analog planes and signals. You want to be sure you keep analog and digital very far apart from one another. Return currents will overlap each other, and if you're splitting the planes, you keep the routing and the return back from the imaginary edge. I mentioned not having a split in the ground plane, but keeping an imaginary edge and keeping everything back from that imaginary edge, just as if you had a split, and then you don't have to have the split, and you can actually have better routing and return paths that way. Part grouping for return. Usually it's the power plane that is divided, and so if it is the power plane, if you can set up the different power families, the different logic families and the voltages in different sections of the board, then you can set up planes within that area, and you can divide those planes, and all of these signals that will route against the power planes in those areas would stay within those areas and would not need to cross over splits. And if they had to cross a split, they would have to go down and go to a solid ground plane, which is one of the reasons we don't want to split a ground plane. So fewer signals to be concerned with if you're putting all of your splits of your power on one layer. If you can do that, it helps to contain everything in one area of the board, and next picture will show you that. Routing will not need to cross splits and return planes, and can flow unabated back to its own source, and the signal must return to their own area unless the return against a solid ground plane, as mentioned. So here's what I was talking about. You have multiple different power layers that are split by these paths I'm having a hard time drawing them, but they're here. And the blue lines that you're seeing are the signals that are actually routed returning against those power layers. You see that they don't cross the splits in those planes, even though it might be a more direct path. It's better to have them wind around and follow the edges of the plane rather than crossing over the splits in the planes. If you have to cross across an area and it is split, can you make an area that is a moat, if you will, between the two sections? For example, in this A to D or D to A converter type situation where you have signals that have to go from one side to the other side, if you can make a moat area underneath the part that is where the grounds are joined together, then the signals can all cross across that particular area instead of having all of them interrupted, if you will, by routing across splits and planes. So try and do that if you can't route across a ground plane in that area. Sometimes there are needs because of very sensitive circuits to actually have a split in a plane. If a partial split is required to protect some slow or very sensitive circuits, then we would want to have it be as small as possible and everything route around the edges, not crossing those splits at all. Another thing that you can do to help is to keep the routing in the opposite directions. For example, your analog over here, or your sensitive, whichever it is, over here would route in this direction, and your digital would route in this direction. The digital would keep its return close by, and the analog would then be able to spread out a little bit in this area up here. And so route them perpendicularly. It helps a little bit. It doesn't help a tremendous amount. It may prevent you having to put that split in the plane. If you have to put the split in the plane, it's just an extra precaution. Layer paired routing. I mentioned earlier we would talk about what layer paired routing was. If a signal or a bus cannot route entirely on one layer of the board, which is the best way for it to route, then it has to transition to another layer. So we'll take a signal from layer whatever and we'll take it to another layer and route it in the opposite direction, but so that we can move the signal into another area of the board. In doing that, we would want to take the signal from the layer that we started on and route it to the opposite side of the same ground layer. If it's returning on ground up here, then we would want it to return on the other side of that ground plane down here. And in doing that, we're keeping it very, very tightly contained, the energy very tightly contained and controlled, and it's all on the same layer, and the energy can easily flow. The return current is the blue, and it can easily flow back to the source following the signal as it goes throughout its routing path. If the return against one plane is not possible, then reference a tightly coupled set of power and ground planes. That means that they have to be within like 8 mils of each other. And if they are within 8 mils of each other, the energy where the signal is going through the via to the other side of, basically it's doing the same thing as the previous slide here. It's just that in this case, the energy can couple between the power and ground plane because they are so close together. You cannot do this with different setups of a scenario, so they have to be very, very close to one another, the power and ground in this case. So, but you also would notice that there is a small amount of energy spread in this particular area. So the signals will spread out just a tiny bit between them, but because they are so close together, it is contained and it is okay to route that way. If you are trying to do this on a 4-layer board that is set up in this kind of configuration, the power and ground planes are just too far apart and it won't work. Or if you set it up in this kind of a situation where the power and grounds are close together, it would probably work, but your signals are too far away to actually be returning on those planes. So neither one of these is a good example of how to set up the stack-up for the board. Nor is this one. This is a 6-layer stack-up, which is just taken this particular 4-layer stack-up and put 2 layers of signals in between them. And in doing so, yes, the signals could route on opposite sides of this plane, but they could not then transfer to this particular area down here because it's referencing power, it's not referencing ground. So you could do that if you just went back and forth with these signals and these signals, but you would not have good interplane capacitance with this particular setup. And so there's a problem with the rest of the energy for the power distribution on this type of a stack-up. If the stack-up routes to another layer pair within the stack, add a transfer via very near the signal to reduce the inductive loop. So that what is happening is the signal is coming this direction and it's going down a via, its own via, to another layer, to another, referencing another plane, in this case another ground layer. And if you put a ground via connecting those two ground layers next to each other, if you put that very close to the signal, then the energy can couple very easily from the signal and the ground, and so the return path can easily follow that trace going back to its source. This only works if the reference planes are the same voltage, in this case ground. If the signal changes layers to reference a power layer, for example, up here you have a signal and a ground, and they are referencing, the signal is referencing ground, and then you're changing it to a layer that references power. That energy cannot couple, the ground via is still there, but the ground via is not connected to this plane, so there is no way to make that helpful, and so there is no way to make that connection easily for the return path. And we'll go into this in the very end. There's a segment where I take the signal and go from layer to layer with it, and so you'll see why this is a problem at that point. But there is a problem when you take a signal referencing one ground and you try to take it and reference power. So be aware when you're routing your signals that you don't want to do that kind of thing, because it could cause a real problem with the return path. If you do that, the low frequency energy, which is like under 200 megahertz, will try to find a nearby capacitor to move through to get the energy back to the source. So you have the signal going down a signal via, changing and referencing to returning on a power layer. The energy is now on the bottom side of the power layer, or in between the signal and the bottom side of the power layer. It's going around the antipad opening, coming back to the top side, and then going up to the connection through the capacitor, and then back to the source. But that's a long path, and it's a long path away from the signal. So that's a problem for the energy to return. It's a split in the signal and its return energy, and that's a problem because that creates some noise in the area that can cause more issues. So the lower frequency energy can do that, but the higher frequency energy, because of the inductance of that device, it simply won't do that, and you won't have, it won't work the way you would like it to work. But it doesn't hurt anything to have lots of extra decoupling capacitors sprinkled around the board for low frequency energy to return back to the source, no matter where it is in the board. So if you're routing your board and you need to change from layer to layer, set up the whole entire board structure so that you have layer pairs, and then your signal can go from layer pair, for example, over here, layer pair here, and then it goes down to a layer pair that's right here, and then maybe it goes back up to a layer pair here, and then up back to the top layer here. See, I've got them marked with the pinkish color on the ends where the layer pairs are, and this is the ground and power that are very close together to one another. So if you can route in that kind of a manner, going from layer pair to layer pair, always keeping in mind where the return path is, then that's the best way to account for the energy for that particular signal and keep it flowing in the manner that you want it to flow. The return current will eventually flow back to the source, typically through the ground pin of the source IC. You can set up stackups that will allow for layer paired routing throughout the part containing energy. So you have a single layer or double layers, and constantly be able to change from layer pair to layer pair, no matter how many board layers you actually have. And you can have, of course, many, Always try to set them up as a layer paired structure so that you're able to get your return to follow the signal back to the source. If you're working with very, very high speed signals in the gigabit range, the power and ground pins should be on the closest layers in the stack up to the IC. That is because you want to be sure that you contain that area to the smallest areas possible. So if you're putting the power and ground on these two layers here for this particular device, then the energy is contained within that very small region. If you put them down away from the part, like in the middle of the board, then there's much more of a loop area that is created, and you have to contain that loop area for the highest speed signals. For regular signals, regular high speed signals, whatever that is, this might be fine, but once you get into the very fast high speed signals, you want to be sure that you're doing everything that you can to help those signals stay clean and nice the way that you want them to be and work the way that you would like them to do. When we are working with the spacing of the signals, we need to be sure that we understand that if we have two different kinds of signals next to each other, or two different kinds of buses next to each other, and one turns on and the other does not, then you can create noise on the one that did not turn on, or you can create noise on the one that is a different voltage of from the other one. And so it's very easy to spread that noise around just because it is a high frequency energy, and it can spread easier. The high frequency energy can spread easier than the lower frequency energy can. It creates greater fields, and so we have greater potential for crosstalk and other kinds of problems. It's not usually a problem within a particular bus to have the signals be close to one another, but it certainly can be when you have two different types of signals or different types of buses or different logic families that can be too close to one another. Return current energy spacing is needed because when we have many signals routed on a layer, there will be many return paths sharing that same plane area. Remember the bell curves that I showed you earlier? You know, they're going to try to interfere with each other if it's an easier path for them to return back to their source. So there is a need for spacing control for return. The receive signals and the drive signals need to have space between them because you don't want them to be interfering with each other. They're doing different things at different times. Bidirectional signals, the same thing. Different voltages and different logic families, the same thing. And fewer spacing issues on internal layers, so you can get things a lot closer on internal layers than you can on external layers just because of the energy spread possibilities. So we want to keep things internally whenever we can. And yes, we're all designing lots of very dense boards using every bit of area that we can to get our signals routed. But we have to think about, if we are designing the board, what is the best for that signal? And if we can't get a good signal path for every signal on that board, then the board probably won't work correctly. And what is the point? The point is that we need to have the best board that we can make, not just the best, not just get the board routed, but the best board that we can make that will work properly. So when a signal happens to be routing, let's say on this particular trace here, the black is the signal, and it's coming, the red is the return path, and it's coming into this area here. Earlier I mentioned the SOICs and them having a problem with the return path. You can see that the return pin for this device is probably down here, or it might be power pin and over here, but either one is farther away from that signal here than anything else is. So it's going to return on the closest copper, and the closest copper will be this signal, and maybe even this signal here, because they're closer to it than anything else. And so if that energy spreads into those signals, now you have the contaminated other signals, if you will. And the same thing with them turning on. And so all of these signals are not getting back to their ground pins or their power pins. The return is not. And so it's creating some potential for problems of overlapping energies, and we don't want that. If there are no pins in the area, for example, if this was just a pin in an area that did not have an actual device hooked to it, or the pins were not close to each other, then it would spread out even more, looking for whatever it could find to get back to its source. If you're working with connectors, you want to maximize the number of power and ground pins for the signal return. To return the energy field spread, the same thing. You have a signal that's the black line is the signal, and it's returning on the layer below it, whatever that is, probably ground. Then you would want this to be a ground pin, either here or very, very close by, so that there is a very close path for that signal and its return path to couple in immediately and stay together. If you are doing something like if this is not the return pin, but the return pin happens to be down here, then if your signal comes into that pin, it's not going to go all the way over here. It simply can't do it. It would prefer take the easiest path, which is close by, and so it's going to choose the signals and the pads and the pins in those areas and create energy on those paths. If we're routing through the layers of the board, and this is intended to show that the signal is here and the closest ground pin is far away, is what this is intended to show, then the signal will come through here and change layers and go down to this layer. In doing so, there is no return via close by, so the energy has to spread out all through this area, looking for another path to get the energy from down here, back up to over here. So in doing so, it will spread out through that area, and the possibility of messing the other signals up in that area is quite high. And so that's why we put the ground vias, if we're returning on ground, we put the ground vias right next to that signal pin on a high-speed signal or a critical signal. We want to be sure that everything is set up to return as easily as possible. Here we have an issue where we're dealing with I/O parts and signals, and we have an I/O driver that's been placed poorly, and it's way across the board from the cable that it connects to. And in doing so, there is a long trace that has to make a connection from one to the other. That I/O signal has a great potential for picking up noise from anything that happens to be nearby. For example, if you place this part here, then any signal, any high speed or anything with extra energy in it could capacitively couple its energy across to this I/O signal. Now it goes out to the cable, and that cable can easily then become an antenna off of this board. And so we don't want that antenna to cause problems to anything in the other area besides the board itself. And so we would definitely want to place this I/O part as close to this cable as possible. Another example of this is if we happen to do this same thing, have the I/O here, and I don't know why that was separated, have the I/O here, and you have that I/O signal going across. Maybe this is the closest signals happen to be not important nets, something of reasonable quality, but that there is high-speed energy coupled to that particular net, let's say down here, and then that energy up here finds that it can couple across to that particular net here, and then again cause problems. So you can see that there's all kinds of problems with placing parts, especially for I/O parts. It's important to keep them very, very compact and close to one another so that there is no possibility of creating energy. This is called cascaded crosstalk by the man who first discussed it, and that's Dr. Bruce Archambault. And what he's saying is the energy can come from someplace else, even if you're careful to only route with something unimportant nearby. It's still not necessarily going to work for you. So be very careful how you route anything that goes anywhere near an I/O section of the board. Guard traces are another thing that some people like to use. In digital, Layers that have a ground plane, they're probably not needed. We simply put in the signals, the green lines, and leave room as if we were putting in a guard trace, and then because they're spread out from one another, they won't couple to one another and there won't be an issue. But if you have something like a 2-layer board without any return planes, then the guard traces may be helpful if they are grounded at each end. But you don't want to necessarily put in ground traces between signals on a multi-layer board, because if you have set up your stack up properly, the signal is going to return on the closest plane, which would be 1 layer away, and it's not going to return on that ground trace, so it doesn't really matter that it's there. It only serves to separate it from the other traces that are nearby. Some current flow from layer to layer. This is the section where we will actually take a signal and we will go from layer to layer, talking about where the signal actually goes. Some of it is more examples of the same stuff we've talked about, and some is a little bit different. So we will take an example of a 10-layer board and follow how the current flows from layer to layer, and discuss what is happening in each layer, discuss the return current, and discuss displacement current. So back on layer 1 to 2, we have the signal that is routing on the top layer in this example, and it's returning down on the top layer of the layer 2, which is a plane, a ground plane most likely. So the energy is contained in the dielectric material between those two. It is not in the plane, it is not in the signal, it is following the trace of the signal. As the signal moves from one side of that plane to the other side of that plane, the signal return can very easily return back around the antipad opening of the via of that part, and then go back to the source, follow the signal back to its source that way. When it gets to that point, the energy is flowing in here, remember? And when it gets to that point that it's flowing to the opposite side of that plane, it's actually compressing down and flowing in the antipad opening between the via, the outside via, and the antipad opening. It is not flowing in the via itself. It is flowing. Remember, the energy travels in fields, and so the fields are taking the energy on the outside of the via and coupling it across to the plane layer that is layer 2. And so the energy is going from this area here down this area here, and then the signal moves on wherever it's going with its return path following. So now it's gone back down to layer 3. And the energy has gone down the side of the via hole as explained, and then it goes around the signal, or the trace itself goes around the via and off to wherever it goes to, and the return path is then in this area here, in the dielectric area of this area here, and the blue line shows you that it can easily return back to the source by simply following the trace and go from one side of the plane to the other side. Once it comes up, you're looking at the antipad opening. On the top side of layer 2, you can see that the energy over here was on the bottom side of layer 2, which is the plane, and it comes around and comes up the edges of the antipad opening to gather together and then follow the signal back to wherever it came from. Now it's on the top. See, over here it was on the bottom because it's darkened, and over here it's back up on the top because it's lightened. So this is just another view, another example of where that energy is flowing. Remember, the current cannot flow through the plane, so it has to have an opening to flow through the plane. And so it flows in the antipad openings. The antipad openings are not large enough to have massive amounts of current flow through them, but when you're taking signals from one layer to the other, they will work just fine for that. For clarity, I will continue to show the signal actually going through the via, even though, as we just discussed, it is out on the outside barrel of the via, between the via and the antipad opening, but it's just easier to show it as going through the via. So understand for clarity what I'm talking about there. Okay, now the signal is going from layer pair of 1 and 3 down to layer pair 4 to 7. And 4 to 7, the signal will then go from the returning on the underside of layer 2 ground, and then it's following the via for the signal down to the top of layer 4. And because there is a ground via next to it, the energy is flowing between the signal and its ground via, and so the energy return can easily go back, following the blue path, back up to the source in that kind of a pattern. If the return via is placed close by, the return current will flow in the dielectric between the signal and the ground via. If it's not placed close by, it will flow on anything that is close by, as shown you in those earlier pictures. The return current energy goes up the outside barrel of the return vias and travels there by skin effect, meaning that it barely will go into the edges of the plane and the return path, the signal, but it won't actually move there. It is not in the copper, it is in the dielectric material between those two things. The return will always spread out looking for the lowest impedance path at its frequency. And if there is no ground return via nearby, then the displacement current will form and will get large, looking for a ground via or a pin. And we'll go into what that is in just a few minutes. So now the signal is going from layer 4. It's still on this layer pair. Layer 4 is now going from layer 4 to layer 7 with the ground and power layer between them. The energy you can see is transferring the red. Look at the red first. The red is going down the via of the part and going down to layer 7. The return current is on layer 6, referencing power, but because power and ground are very, very close together, it can spread out just a little bit and get to the other side of the ground layer and then return following back the signal back to its source. So this is all fine at this point. You know, it's good routing and return. What happens is that when that signal goes through that via, the return is now on the underside of the power plane. It couples around the edge of the power plane to the top side of the power plane, spreads out as much as it needs to couple to the ground plane, which will be a small amount of spread because they are very close together, and then it will couple around the edges of that ground plane to the top side of the ground plane, and then can easily follow the signal back to its source wherever it was coming before that. When the signal now moves from layer 8 or 10 to layer 8 or 10, things get more complicated. The signal return on layer 7 referenced power, and the signal on layer 8 or 10 would reference ground. So how will we go from the signal referencing power to referencing ground? The energy cannot couple across because you have the ground via, but the ground via is not going to help you because the energy here is returning on ground power, and so there isn't an easy way for the energy here to be able to couple across and get back to the source. There isn't enough copper involved between the edge of the power plane and the ground via to couple across the energy to get that energy to go up the ground via. So there isn't any way to do it that way, and there isn't any way with the energy to couple across from power to ground because they're simply way too far apart. So it forms what we call displacement current. Displacement current is when the current cannot directly flow from one plane to the other, and a charge has to build up on one plane until it is large enough to capacitively couple. Like a capacitor, remember, they have to spread out and they have to spread across, and so the charge will have to build up before it can couple across from one to the other. There is always displacement current when a signal and a return are separated, and the return vias, and when the ground return vias are very close, the effect is minimized. So here we have a signal, and it has no nearby ground vias. It's between power and ground. The signal up here is referencing the ground layer here, and then it's going down to a layer down here that is returning on the bottom side of the power layer here. And so that energy then can couple across from the bottom side up the antipad opening to the top side. But now how is it going to get from there to there? And this is the problem. This is where a lot of the noise is created, because the energy up here on the top side of this power layer has to spread way out in order to get enough energy to capacitively couple up to the bottom side of the ground layer and then be able to go from there back to the source. So it couples a large amount of energy. This is the displacement current. This is the current that is cannot make a direct connection from one to the other, and so the energy will have to spread way out until it has enough charge to get from one to the other. So this is when you have ground and power as the two planes. When you have two ground planes, but there are no nearby ground vias. Let's say there's one not so close, but not terribly far away. It will do the exact same thing with the displacement current, but it will also use any ground vias that happen to be in the not so close range, so that it can get some energy up the outside of that via barrel as well. So it will use a combination of the ground via and the displacement current to get that energy back to the source that way. Displacement current will spread as far as it has to in order to build up enough charge to get to the other plane. And this path is the higher inductance, the longer loop area path. And it can cause all kinds of noise in the planes, and it can cause all kinds of noise in the signals. It can interfere with anything that happens to be in that region. For example, here is the same setup that I showed you a couple of slides ago, where you have a ground layer here, here, and a power layer here. And now let's say this was like a 6-layer board where you had signal, ground, signal, signal, power, signal. Then these layers are also routing in here, and they're also being influenced by the energy that's happening to try to couple across from the top of this plane to the bottom of this plane. If there's any routing in this area, it's also going to be influenced by all that stray energy that's in that area. And so we want to keep that as minimal as possible, that we take that kind of routing approach to putting signals into the board, because it creates lots of common mode energy. Common mode energy is basically stray energy that can couple to anything that's on the board itself and cause problems with any signal that happens to be on the board. These are some references that I used within the return, within the presentation here. I hope that some of this shows you that it is not just a random thing, the way we set up our signals, that we have to be prepared for how the energy, the return energy is going to flow, as well as how the signal will flow, and make sure that we're giving it a good path back to its source. Here's a quote that I really like: read books, not app notes, because it's important to read the physics, and it's important to read the people that really study the information of what's going on the board, the Dr. Bruce Archambaults and the Dr. Hubing and those kind of people, so that they can give you ideas of what's going on. And the app note is just telling you what they think you should do on that particular part on that particular board. And if you don't know the particulars of the stackup that they put on the board, or the way that they routed that particular section or whatever, then you're not necessarily getting the best information. So read the books so that you know what to do without reading the app notes, and then read the app notes when you're designing the board to see if that information applies. And that is the last of it. At this point, if you have any questions that you would like to discuss, otherwise the presentation will be up on the YouTube channel for Altium. And
yeah, thank you so much, Susy. That was fantastic.
Thank you.
Yes, we do have some questions. One is from George de Castro, and his question is: can we play with ground vias to play with the current loop, trying to reduce the path? With the current loop to reduce the path.
Well, you always want the ground via to be as close to the signal if the signal is changing layer with a via, you always want the ground via to be as close as possible to keep those two very, very close to one another, so that that energy, remember, the energy is going to be between the two vias, in the dielectric material between the two vias. And if they're not close to one another, they can't couple to one another, and so they will have to spread out into anything that's in that area, and it could be a large loop area that they end up spreading to.
Thank you. I hope that answers the question. The next question is by Lorenzo Carelli, asking, does EMI shielding make a big difference with high frequency signals?
Yes, we would like to keep as much shielding as possible. I had a slide in there that showed that we would possibly put planes on the outer layer of the board, and that does help to contain that energy. As you saw in the early slides, there was one signal that was close to a plane on one side and open in air on the other side. And if you have, I mentioned, if you have two planes on either a plane on either side of that layer, that signal layer, that would keep that energy even more contained. So having a plane on outer layers of both sides of the board very much keeps the energy contained within the board itself. It can still leak out. There's still high frequency energy that can get out, but it is a big help to the stack up. Yes.
Thank you. There's another question by Lorenzo Carelli. Which PCB have less interference, flex PCBs or solid PCBs like FR4?
I would think probably, and this is a total guess, but I would think probably flex, because the layers are closer together. But if you're dealing with HDI, you have a solid PCB that has layers that are very close together. The point is that they have the signal and its return path very close together. So it's how you design either one of those boards, as opposed to whether the board actually is better this way or that way. So I would say the bottom line is to keep them as close to each other, the plane and the signal as close to each other as possible.
Okay, thank you. There's one last, it's not really a question, it's more like him wondering. MR is asking, so he had some crosstalk at the beginning of his career, and he's wondering if trying to damper the rise and fall time by applying a passive component, for example a capacitor, can help.
I would put a termination resistor in series with it, rather than to limit the voltage of that signal. That's what, it's mine, sorry. It would limit the voltage that is drawn from that plane, and so it would limit the signal rise, and then the signal would then go down the path to the load, and then double in voltage at that point, and then be able to turn anything else on that line. And so it's easier to do it that way as opposed to capacitively doing it.
Okay. Yes.
All
so
right.
That were all the questions. Thanks everybody for tuning in. If you found this useful, we will have another session coming up in just a little over 2 hours. Make sure if you find this useful and you think it can help your peers and friends, to share the link that I posted in the live chat just some moments ago. Make sure you shared it, and check out our YouTube channel for more content. We just posted all the sessions from Altium Live. I think that will be very interesting for you as well. And yeah, subscribe for anything that comes up in the future. We have so much more to come. Yeah.
Okay, thank you very much everybody, appreciate it.